speeding up because they're accelerating. So we start move. We know we're going to end up going in negative direction. So we start slow, and then we start speeding up, and then it hits the ground, and a little time later it's now coming back up in the positive direction. So it's coming back up to where it started, but it's coming back up, and it's coming back up at a huge rate of knots to begin with, but then it's slowing down, and then it's back as it's caught. Here we go. Juliet throws a ball. I don't know if you know the story of Romeo and Juliet. So Juliet is on a balcony, and Romeo, because he's not allowed in the house because the families don't like each other, Romeo comes along and starts yapping at Juliet from the ground, and it's all very Shakespearean and nice. Anyway, in this day and age, Juliet is a hardcore physicist, and she's a strong feminist. So Juliet doesn't sit on the balcony all day. Romeo's up on the balcony, and Juliet is having a night on the town, and then she comes back and decides that she's going to start throwing a ball at Romeo, who's stuck inside, and they're going to start playing catch or whatever. So Juliet throws a ball up to Romeo at his window, who catches it. Speed time graph. So this is a vertical motion. So as this ball leaves her hand, it's going fast in its positive direction, but as it goes up, it slows down, and this is the point where he catches it. Now, if he were to miss it, we've done this bit in blue, then it's going to start speeding up, but in the negative direction because it's going down the way. Here we go. As soon as it leaves Juliet's hand, then the influence on it is going to be negative 9.8, and it's going to be a steady influence. If you were to miss it, then I've done this in blue, then there would still be a negative 9.8 meters per second squared influence, and it would carry it down. So displacement time graph, it's leaving her hand. If the hand is the origin, then it's leaving the hand at a big rate of knots to begin with, because it's going fast as it leaves the hand, but that big rate of knots slows down, and this is the top of the flight. Now, this is where we said he catches it, but if he were to miss it, then it's at 0 here, and then it slowly starts picking up, going faster and faster towards the origin, which is her hand, until it gets there. So the kind of gradient gets steeper and steeper. Alright, so displacement time graphs. They take a bit of thinking about, but just do your best. Momentum. Momentum is mass times velocity. Momentum is mass times velocity. You would maybe think that there should be a unique unit for momentum, but there isn't. So therefore, units of mass are kilograms, the units of velocity is meters per second, therefore the units of momentum are kilograms meters per second. Maybe we should invent a unique name for the units of momentum. Anyway, formula sheets, P equals mv. So you might think, what the hell is the point in having this new quantity to do with speed when we already have speed and we've got kinetic energy as quantities to do with moving stuff? Well, the answer is momentum is a quantity which is conserved, meaning it stays the same in far more situations than kinetic energy is. And this lets us find out stuff. In physics, we love quantities that are conserved because we can have two different situations, and if there's a quantity which is the same in each situation, then it allows us to work out stuff. If we know lots of stuff about the first situation but only some stuff about the second situation, then from the first situation we can find out the quantity which is being conserved, and then we can say, well, this quantity is still being conserved in the second situation, and we can use that to find out whatever it is we're missing in the second situation. So that's the point. Momentum is conserved far more often than speed and kinetic energy. So what is this conservation of momentum? Well, without an external force acting, the momentum of an object cannot change. Sort of makes sense, doesn't it? So even if two objects collide, if there aren't any external forces acting, then the total momentum after a collision between the two will still be the same as the total momentum of the objects before the collision. Because if the only thing which can change momentum is an external force, and you've got two things moving towards together but there aren't any external forces, then even if they smash together and things look very different at the end compared with what they started with, if there's no external forces, then there's going to be no change in momentum. I know when these two hit, then there's going to be like, they're going to smash up and whatever, but that's not an external force, that's a sort of internal force between the two. So if there's no external force, then total momentum can't change. It's a conserved quantity before and after. And this lets us easily calculate stuff. So the top tip with momentum questions is to draw out the situation before and draw out the situation after. And you know that with momentum, it's mass times velocity. And so make it clear on your diagrams what the mass of the objects are and what the velocity of the objects are. So here we have a gun with a bullet in it. And the gun gets fired and the bullet shoots out. So the situation before, you've got a 5 kilogram gun and you've got a 0.004 kilogram bullet inside, and they're both at rest. After the gun is fired, the bullet gets flung out at a speed of 150 meters per second, and we want to know the speed of the recoil. If you've ever shot a gun, you know that there's recoil and the gun sort of kicks back in your hand, and we want to find out the recoil speed. So to do these questions, we say, well, we remember the conservation of momentum. The total momentum isn't going to change. So the total momentum before the change equals the total momentum after the change, because there's no external forces acting. Yes, I know, you pull the trigger and it goes bang and there's a force which shoots the thing up, but that's an internal force. There's no external forces. And at higher, whenever you do this, it will be with no external forces. So momentum is always conserved. So the total momentum before equals the total momentum after. Because because the bullet is flying out to the right hand side, we're going to choose going to the right to be the positive direction. So momentum before is going to be mass times the starting speed of the gun plus the mass times the starting speed of the bullet, and the momentum after is going to be mass times the finishing speed of the gun plus the mass times the finishing speed of the bullet. So the mass of the gun is 5, starting speed is 0, so 5 times 0, and then the mass of the bullet is 0.004 and the starting speed is 0. Mass of the gun stays as 5, the final speed is v, we don't know what that is, and the mass of the bullet is 0.004 and the speed is 150 meters per second. This on the left comes to 0, this on the right is simplified to that, and if you solve that, v, the velocity of the gun, turns out to be negative 1.6, which just means it kicks back in the negative direction. Remember, you've said that going to the right is positive, so this tells you it kicks back in the negative direction. So part B of a question is quite often show whether this collision or whether this exchange is elastic or inelastic. So if you've got two things coming together, two cars, and they're going to smash together, to show whether it's elastic or inelastic, what you have to do is you have to find the total kinetic energy after the smash, and you have to find the total kinetic energy before the smash. So that's Ek equals half mv squared for each of the things involved. Now, if the collision is elastic, then the total kinetic energy after the collision equals the total kinetic energy before the collision. Not many collisions in real life are elastic. So gas molecules hitting the sides of rooms, that's elastic. The total kinetic energy after is the same as the total kinetic energy before. And you can get roughly elastic collisions between two carts in a classroom on a air track coming towards each other if you put magnets on them, but make sure you've got two south ends facing together or two north ends facing each other so they don't actually touch. The magnetism repels. That's almost an elastic collision. And the air molecules are an elastic collision, but most stuff in life, most collisions in life are inelastic. And in an inelastic collision, the total kinetic energy after the collision is smaller than the total kinetic energy before the collision. So you imagine like a car crash between two cars, then obviously the kinetic energy afterwards tends to be 0 because they come to a halt and so that's an inelastic collision because the total kinetic energy after is less than kinetic energy before. Again, much as conservation of momentum questions, the key is drawing a picture. Always draw a picture with the whole kinetic energy stuff, or you might be able to use the picture before. This thing actually is an example of explosive action because the kinetic energy of the system, the total kinetic energy of the system afterwards, is bigger than the total kinetic energy before. So this is an explosive event. The kinetic energy after total kinetic energy is greater than before. It's an explosive event. An elastic event is if the total kinetic energy after is the same as the total kinetic energy before, and an inelastic event is if the total kinetic energy after is smaller than total kinetic energy before. Now, let's move away from situations where there's no external forces. If there are external forces, then momentum is going to go up or momentum is going to go down, depending on the direction that that force is applied. So, imagine something trundling along with a certain amount of momentum. Well, the only thing that can increase or decrease the amount of momentum that that object has is an external force acting on that object for an amount of time. And an external force acting on an object for an amount of time is called an impulse. An external force acting for a certain amount of time, in other words an impulse, will change the momentum of an object. Change in momentum. How do you work out the change in momentum? It's mass times final speed minus mass times starting speed. So, because an impulse is a force for a certain amount of time, impulse you can work out by saying force times time. They're one and the same thing. Impulse causes a change in momentum. So if you work out the change in momentum, you've found out the impulse. So that is impulse, it's also a change in momentum. This is impulse, it's also a change in momentum. If a question gives you stuff about masses and final velocities and initial velocities and asks you for the impulse, then you do mv minus mu. If it gives you force and time, then you can work out the impulse from that. Okay, so these things are pretty much the same because one causes the other. Because one leads to the other, you can also just equate the two. So force times time is mv minus mu, and that's the version which is on the formula sheet. Now, if you're thinking about the effects of the force on something, and it's usually in terms of how damaging the application of this force is, then you're wanting to make F the subject of this equation. If you make F the subject, then you say F equals mv minus mu over t. So if we're thinking about the effect of this force on the object, if for a given momentum change t is small, so the thing on the bottom of the fraction is small, then F is going to be really big. And the opposite is true. If t is really big, then F comes out to be really small. This is the principles of airbags and seat belts versus windscreens. If you're in a car smash, then you are going to be losing momentum. If you go through the windscreen, then that windscreen is going to take a very short amount of time to get rid of your momentum. If t is very short, then the force on you is going to be really, really big. The whole principle of a seatbelt, and in particular an airbag, is that this momentum which you are going to lose, that is non-negotiable, but this momentum change which is going to happen to you, and it's non-negotiable, is going to happen over a longer amount of time, because an airbag is much more flexible and than a windscreen, it takes longer to slow you down, and if t is longer, then force is smaller. Alright? There's a third and final way of finding impulse or change in momentum, and this is if we have an impact graph. So we can graph the previous concept. If we have an impact graph of the force which is being applied to an object to change its momentum,